Hello, my name is Juan Martínez. I performed a 3.5-month stay at ESI Group in Angers and Paris as part of the Marie Curie Rice Project Cometas that took place split into two periods, from June 2024 to August 2024 in Angers during the first period, and in July 2025 for the second period in Paris. I will summarize in the presentation the work done and the relevance into the research line of metamaterials I lead at INTA. I will briefly talk about my educational background and professional experience. I became an aeronautical engineer in 2005 after finishing my 5-year degree studies at Polytechnic University of Madrid. Sometime later, I got an additional degree in mathematics in the Spanish National Distance Education University, and I obtained my PhD diploma in 2016 in the same university of my first degree in aerospace engineering. My professional experience started with some internships, both in Spain and abroad during my last years of the university, all related to aerospace engineering. I started working at INTA in 2005 in the Department of Structures and Mechanisms, where I continue nowadays with the current position of staff researcher. I am also part-time lecturer in the University Polytechnic of Madrid. More detail can be found in my OrgKite profile. I complete in July 2025 a 3.5-month secondment at ESI Group under the Cometas program that was split into two periods, being the initial period performed 1 year before. This stay contributed substantially to both the project goals and benefits my professional growth and research. During these periods, I contributed to Work Package 5, specifically Task 5.2, focused on developing code to allow the dynamic characterization of metamaterial lattices, and advancing in the design of experiments needed for feeding the surrogate models that will provide the computational time savings needed for this dynamic characterization, and finally obtain the lattice design of the prototype. My work was compiled into a report and this presentation, thereby contributing to the project and reinforcing my communications skills. The impact on my career is also significant, as the collaboration with ESI Group researchers strengthens my connections within the international scientific community, and the knowledge gained is remarkable for the ongoing line of research I lead at INTA. In short, this secondment was a valuable experience that contributed to my knowledge, improved my skills, and allowed me to establish collaboration for further impactful research in metamaterials. As previously mentioned, my work is related to mechanical metamaterials, lattice-based metamaterials. Mechanical lattice-based or cell-based metamaterials are micro-architected materials whose unique mechanical properties arise primarily from their designed structure, specifically from the periodic arrangement of a unit cell in space to create intricate 3D shapes. These materials offer great potential for aerospace and automotive structural engineering applications due to their porosity and low density. The repeating pattern of unit cells may enable the manipulation of mechanical waves so that the attenuation of vibrations can be achieved. Variation in the unit cell design yield a wide range of tailored properties, including exotic ones absent in bulk materials. The pursued goal in this study is the attenuation of vibrations, one of the challenges in spacecraft design. The vibrations from diverse sources affect negatively to the payload or other sensitive components, which leads to performance degradation. These harmful vibrations can start in the range of micro-Gs and at very low frequencies, as low as 0.1 Hz. Structural integrity is not affected by micro-vibrations, which are studied separately to characterize their impact on the performance demands of the payload. With the use of metamaterials, we can address both problems of micro and regular vibrations with a common approach. Dispersion diagrams are the method to study the mitigation of mechanical waves for a given metamaterial based on a unit cell. This diagram allows to identify if there is any range of frequencies where the mechanical waves interfere constructively across the material, so that this interference reduces the amplitude of the propagated wave, which is called bandgap. It indicates that a finite array composed of these unit cells will be able to mitigate mechanical waves whose frequency falls in that range. Through the combined efforts of the work carried out during the first period of this secondment and that of another researcher within the COMETAS project, a developed tool made by both of us has been validated for producing dispersion diagrams of a generic unit cell using a commercial finite element method software, which is a regular requirement in aerospace projects. During both periods of the secondment, the design of experiments for creating the surrogate models has been made. The geometry and the most relevant parameters have also been selected. The final geometry that has been used for the unitary cell in order to obtain the dispersion diagrams, the one shown in the right of this slide, is based on an array of 2 by 2 by 2 basic unit cells, the one shown in the left. This assembled cell has different parameters applied to the basic unit cells in pairs, involving almost 1,300 different combinations or cases that have been solved. Just to show the computational requirements needed, each case, this is each dispersion diagram obtained, requires a minimum of 40 normal modes analysis in order to compute all the different possible directions and wave numbers of a plane mechanical wave transmit through the cell, what is plotted in the horizontal axis of these dispersion diagrams. A sampling of the performed design of experiments is shown in this slide, where it can be seen that for different parameter values, the results are affected both qualitative and quantitative. In other words, the width of the bandgap and their upper and lower frequencies. These selected cases show a unique bandgap per case, but some other cases show either no bandgap or more than one bandgap. The goal of the surrogate models is to deliver the bandgaps associated to a specific combination of the cell parameters without requiring the high computational times needed for creating the dispersion diagrams. To summarize, during this work, a Python code was developed to generate dispersion diagrams using Nastran software. This code is versatile, so that any finite element model mesh available can be now used to do it automatically, creating the congruent nodes for imposing the flocked blocks boundary conditions. The key parameters for the goal of obtaining bandgaps have been also identified, parameters that we can later control thanks to the additive manufacturing methods used for creating these structures. A unitary cell has been designed and the data has been generated, so that the methodology for creating an effective surrogated model can be now validated. This validation is currently an ongoing task. As a result, a great number of parametric cases can be solved, and this data can be used to create surrogate models. The work done during this period lays the foundation for future advancements focused in the mechanical waves attenuation. The planned tasks for the future are validation of the selected parameters bounds and the associated design of experiments, development of resilient surrogate models, identification of the most appropriate cell parameters for achieving a specific bandgap related both to the geometry or the material of the cell, and once complete the final validation and some planned additional tasks, to submit a journal paper based on this research. Finally, I would like to thank the European Union Horizon 2020 Research Program for the opportunity to carry out this secondment, and also to Professor Chinesta and his research group, particularly to Amin and Javad for his welcome and support during this secondment. Thank you very much for your attention.